So in this class, we will discuss about two things, that is one polar coordinates, another one is cylindrical coordinates. So till this we have learned some of the topics in Cartesian coordinates. So in Cartesian coordinates you have two things, two types, that is one is two-dimensional, wherein you have only x and y components. In three-dimensional Cartesian coordinates we have x, y, z coordinates. Now coming to polar coordinates, so normally these polar coordinates are used to analyze some plane stress or two-dimensional problems which have curved boundaries. So sometimes the elements, when you divide the structural member into so many elements, so some of the elements you may have curved boundaries. So when curved boundaries come into picture, then you can go for this polar coordinates. Here, this is the element I have taken, curved element, whereas these two are having curved boundaries and this is straight boundary. So in the case of polar coordinates, so you have this one angular dimension, one linear dimension. So here R is the radial direction, theta will be in the angular direction. So R and theta, they are the coordinates in they are the polar coordinates, two-dimensional thing. So here, in this case, what happens? First, you should understand what is the relationship between your Cartesian coordinates and polar coordinates. In the case of Cartesian coordinates, we take as x and y. In the case of polar coordinates, we take the coordinates as r and theta. The relationship between x, y, r and theta can be explained using this sketch. Suppose if you consider a point P here in a two-dimensional element which coordinates x and y, this becomes x, this becomes y, and this radial distance is r, and this angle is theta. Now, from the trigonometric relationship, you can write tan theta as y by x, or you can say cos theta as x by r, or x is r cos theta, sin theta as y by r, or y is r sin theta, and now this r square is equal to x square plus y square according to Pythagoras theorem. Now, this is the relationship between r, theta, x and y. So, radial direction will be in this direction and angular direction will be perpendicular to that. That means, if you take this as the radius of the circle, so this tangent which is drawn perpendicular to the radius, that represents the angular direction. Now, if you consider a curved element like this, I will take this distance from this origin to this as r, and the thickness of the element as dr, and the angle made by this element with the origin as d theta. So now, according to trigonometry, this length of this arc of this circle, becomes r into d theta. That you know. So area of this elemental area of this curved element can be taken as, this can be taken as a rectangular element which is length into breadth, that is r into d theta into dr. So r into d theta into dr becomes the area dA. So in analyzing problems with polar coordinates, the elemental area is always taken as r into d theta into r, or r into dr into d theta. So this you should remember. Whereas in the case of Cartesian coordinates, elemental area becomes dx into dy. Here it is r into dr into d theta. Now, just similar to your Cartesian coordinates, two-dimensional Cartesian coordinates, you have in the polar coordinates, once again you have three stress components which are denoted as sigma r, sigma theta, and tau r theta. So just recall that in the case of two-dimensional Cartesian, it is sigma x, sigma y, and tau x, y. Here it is sigma r, sigma theta, and tau r theta. So sigma r is the radial stress. You can say it as radial stress, or the normal stress acting in r direction. Sigma theta is the normal stress acting in the circumferential direction, that is which is perpendicular to the radial direction, and tau r theta is the shear stress which acts parallel to the area. Now here, so similar to this stress components, you have the corresponding strain components also. Just like epsilon x, epsilon y, gamma x, y in 2D Cartesian system, you have in polar system, you have epsilon r, epsilon theta, and gamma r theta. So epsilon r is the normal strain in radial direction, epsilon theta is the normal strain in the theta direction, and gamma r theta is the shear strain. So these totally you have three stress components and three strain components in the case of polar coordinates. Just you can compare this with this your two-dimensional Cartesian. So sigma x, sigma y, tau xy. Here it is sigma r, sigma theta, tau r theta. So x is replaced by r, y is replaced by theta. That's all. Now, if you derive the equilibrium equation which we have done in the case of Cartesian coordinates two-dimensional, so we got some equilibrium equations, two equilibrium equations. Similarly, here if you derive for in terms of polar coordinates by taking an element, curved element like this, and by applying the stresses in all the 6 phases, and if you write the equilibrium equation by converting all the stresses in terms of forces and simplifying, we get these two equations. So just practice this equilibrium equation derivation which I have given in the notes. So here just you have to be careful here. This is not symmetric. In the case of Cartesian coordinates, so these equilibrium equations you can write because it follows the cyclic order. X is replaced by y like that. But here, since r is linear dimension, theta is angular dimension, you cannot write in the similar manner. So the first equation is sometimes by taking the forces acting in r direction, and second equation is sometimes by taking forces in the theta direction. So these two are the equilibrium equations which have to be satisfied to keep the body in equilibrium. And please note that F1 and F theta, they are the body force components in r and theta directions respectively, which we have used it as Fx and Fy. So here, see, dou sigma r by dou r plus 1 by r into dou r theta by dou theta plus sigma r by sigma theta by r plus Fr is equal to 0. You can observe here that wherever theta term is there in the denominator, so it will be accompanied with 1 by r term. Please note that. So denominator theta, dou theta is there, so 1 by r term is there, and this is an additional term. Next, the second also you can see here, first one it is theta, is the denominator, so 1 by r term is there. So wherever r is there, then 1 by r term is not there. So this is the additional term. So you can derive this. So if they give a problem, numerical problem on this, then you have to remember this. You have to remember these two equations. So the problem may be finding this Fr and F theta. Or they may give a set of stress system. So sigma r, sigma theta, tau r theta they will give. They will ask you to check whether the equilibrium equations are satisfied or not. If at all equilibrium equations are not satisfied, then what are the corresponding body force components that we have to apply or required to keep the body in equilibrium? That means we have to find out Fr and F theta. So in a given problem, they will give sigma r, tau r theta and sigma theta. So those three components will be given. Please note that all those three, they are functions of r and theta. So this sigma r, sigma theta, tau r theta, they are all functions of r and theta. So they will give that some partial differentiation you have to do as usual. What we did in the case of Cartesian coordinates, same procedure is followed. So since there are functions of two variables, you have to take partial differentiation, and when you are differentiating with respect to r, theta should be taken as constant, and when you are differentiating with respect to theta, r should be taken as constant. And once you differentiate and substituting these two equations, so if the RHS without this Fr is 0, then body force component is 0. If RHS, if you simplify this entire thing if you simplify after substituting all the partial derivatives, if it is not coming 0, then Fr will have some value, F theta also will have some value. So those values you have to find out. So we have done problems in Cartesian coordinate. So similar problem may be given in polar coordinate. Now this is about polar coordinate. That means only two coordinates will be there, r and theta, one linear and one angular. Now we will be having one more called cylindrical coordinates. Of course, cylindrical coordinates problems they will not give. So just you have to understand what do you mean by cylindrical coordinate system. It's a three-dimensional. That means x, y, z is there in Cartesian. Like that, three-dimensional cylindrical coordinates. So two-dimensional cylindrical coordinates is called as polar coordinates. In three-dimensional cylindrical coordinates, you have these three, r, theta, and z. That means two are linear and one is angular. R and z are linear coordinates. theta is the angular coordinate. So element will be taken like this. Please see here. This is three-dimensional element. Three-dimensional element which is defined with two linear dimensions and one angular dimension. So this is the general case of three-dimensional element, and in this case you will be having six stress components. So just like three-dimensional Cartesian, you have sigma x, sigma y, sigma z, tau xy, tau yz and tau zx. You have here sigma r, sigma theta, sigma z, tau r theta, tau theta z and tau zr. So x is replaced by r, y is replaced by theta, z is same. So z is same only here. So this is how we are going to show three-dimensional cylindrical coordinate axis. Now in this case, if you derive on similar lines, you are going to get three equilibrium equations, because it is three-dimensional. You will be having three equilibrium equations. But anyway, from the examination point of view, this is not there. Only you have to practice this one, two-dimensional polar coordinate derivation. So this just for your information I had given. So suppose here also F1, F theta and Fz, they are the body force components along r, theta and z directions. So they may, if they give these stress components, these six stress components, once again they are all functions of here they are all functions of r, theta and z. So three variables are there. So if they satisfy these equations, then we say that the body is in equilibrium. Otherwise, you have to find out the corresponding body force components which keep the body in equilibrium. That is F1, F theta and Fz. So this is about cylindrical coordinates, three-dimensional, and polar coordinates, two-dimensional. Now in the next class, we will discuss some more concept about this polar coordinates and the problems related to polar coordinates and all. And also we have to discuss about strain displacement relationships and compatibility conditions. So next class we will discuss about compatibility conditions.